right, so we've produced section 5.3, which is your last section for chapter 5. This one is about working with regular polygons. So we're going to talk a little bit about what a polygon is and then 2 formulas you can use when you're working with them. So first thing is what a polygon actually is. Polygon is a closed figure formed by joining 3 or more line segments at their endpoints. All the line segments must lie on a plane. They are classified according to the number of sides, and some common polygons are listed in the following table. So basically, it's any 3 or more sided shape that's flat and closed. So the lines have to meet back up again. So this over here, definition of a polygon. The hardest thing about working with polygons is knowing how many sides they have from the names. Okay, these are something you have to memorize. If any of you guys did Science 20, Science 30, probably Science 10, Chem 2030, maybe even Bio, some of these prefixes should be familiar to you. The chemistry prefixes are the same as some of the math prefixes. So in the chemistry stuff, from 5 and higher is the same. So penta meant 5, hex was 6, hepta is 7, octa is 8, nona is 9, deca is 10. The beginning ones are different though, but everyone knows 3-sided shape is a triangle, and then a 4-sided shape is a quadrilateral. We learned that one in the last section. Okay, so you have to be able to recognize from the name how many sides it's going to have. So make sure you're familiar with this chart. Make sure you're familiar with these names. The other little trick to polygons is if all the sides of the polygon are equal and all the angles are equal, it's called a regular polygon. This idea of everything being equal and being called a regular polygon is helpful because it means when we have a regular polygon, we can actually work with some formulas in order to solve for the number of sides or the angle measurements of that polygon. The formulas only work for a regular polygon though. So you have to make sure that it's a regular polygon, and it will say that right in the question, or it'll show you on a diagram that all the sides are equal using those little hash marks. Okay, so when you look at a picture like this, there's a whole bunch of different polygons. There's triangles in it. There are 1, 2, 3, 4, 5, 6-sided shapes, so hexagons. There's 1, 2, 3, 4, 5, 6, 7, 8. There's an octagon. There's lots of different sizes, lots of different shapes. None of these, except for maybe the octagon, look like they would be regular polygons. It looks like the octagon might have all the same side lengths. You can't tell just by looking at it. You'd have to measure it. Okay, so here's the start of how we work with this. It says, what are the sizes of the interior angles of a regular hexagon? So if you just had a question like that, you weren't given anything else like the solution gives you, you'd want to start by drawing a hexagon. Hex means 6. So you're going to want a shape that has 6 sides. If you're a good artist, it'll end up all being the same size sides. If you're not, you're going to have to pretend that they're all equal. It does say the word regular, so they should all be the same size. But when you're working with it, just a sketch is good enough. Just keep in mind they should all be equal. So the solution says a regular hexagon is a 6-sided figure with all sides of equal length. Join your pairs of opposite vertices. They'll meet at the center of the hexagon, forming 6 triangles. So if you drew your hexagon, your 6 sides, whenever we're talking about the sum of interior angles or anything really about interior angles, we want triangles because we're used to working with triangles. So we can turn our hexagon into 6 triangles by matching up the opposite corners. When we do that, we end up with 6 triangles, and all the bases of those triangles are the same size because it's a regular hexagon. The rest of this explanation, the rest of this example, isn't the way you're actually going to do this. It's showing you where your formula comes from. So it says the sum of the angles of a triangle is 180 degrees. Calculate the sum of the angles in the 6 triangles. So I have 6 triangles. If I add up the angles inside of those 6 triangles, each one has 180 degrees inside of it. Multiply them together, it's 1080 degrees. This, though, includes the angles at the center, which form a full turn of 360 degrees. So when I'm adding up my angles in my triangle, I've got this angle, and this center one. And then this angle, and this center one make 180. And then this, and the center. When it's talking about in the question, though, it wants the interior angles of the hexagon. And if I look back at just the hexagon, my interior angles of my hexagon are this piece, this piece, this piece, this piece, here and here. I don't want those center angles. They're not part of my hexagon. I drew them on after. So I'm going to take away this 360 degrees that I added up when I added up my 180 degrees for the triangles. So I'm going to take my total, subtract the 360 in the middle, and it leaves with 720. What that means is all my little outside x's are going to add together to be 720 degrees. So this is the sum of the interior angles in a hexagon. Since all 6 interior angles are equal, we divide by 6. So we take that 720 degrees, divide it by 6, and it tells you that each of the interior angles of a regular hexagon is 120 degrees. Okay, this is the way we do it by forming triangles. Luckily, there's a formula we can use, the sum formula, in order to calculate this, and you guys are going to be given that sum formula on your test. It's not something you have to remember. Using the sum formula is way easier. The formula says the sum of the interior angles equals 180 degrees times n minus 2. And in that formula, n is the number of sides. So this n right here is the number of sides. Okay, so off to the side, I'm going to use my formula to see if I come up with the same answer as the top example did. My formula says that the sum is equal to 180 degrees times n minus 2. And I'm talking about a hexagon, so n is 6. So I'm going to do the sum of my angles equals 180 degrees times 6 minus 2. And when I put this in my calculator, I'm going to be extremely careful. Those brackets need to be there, or I have to solve what's inside the brackets first and then multiply by 180. This is my order of operations. Brackets, my BEDMAS, brackets come before multiplication and division. So I'm not going to do 180 times 6, press enter, and then do minus 2. I'm going to do 180 bracket, 6 minus 2 bracket, and then it's going to give me the right answer. If you do it the other way, it's absolutely going to be wrong. Your calculator will do it in the wrong order. So I'm either going to type it in exactly the way it is, or I'm going to simplify first and say that the sum is 180 degrees times 4, because 6 minus 2 is 4. 180 times 4 is going to give me 720 degrees, which was the same number I got for my total in my example. Then, because I'm talking about individual angles in my question, I want to divide the sum, the total, by the number of angles there are, which is also going to give me the same answer, 120 degrees. So really, there's 2 formulas you can use. There's this sum formula, if you want the total added up of your angles, and if you want the size of an individual angle, we can modify this slightly. We can say that an individual angle equals the 180 degrees times n minus 2 divided by the number of sides again, or the number of angles. which is just what we did over here in this last step. We divided by the number of sides. So if you want to do it all as one formula, instead of having to think about what you do next with the sum, you can use your sum to find all of them added up together, or you can use this individual angle formula in order to find the size of one specific angle. Keep in mind though, in both of these formulas, it has to be a regular polygon. If it's not, they don't work. You cannot use them. Okay, so these are your two formulas. You're going to work with them lots. They'll both be given to you on a formula sheet for your test. It doesn't explain how to use it though. It's not going to tell you that n equals the number of sides, so don't forget that. That's important. Okay, so the next question says that Melanie says that since a dodecagon has twice as many angles as a hexagon, the angles in a regular dodecagon will be half the size of those in a regular hexagon. Is she right or wrong? Calculate the size of each of the angles of a regular dodecagon to verify your conclusion. So hex means 6. This is the one we just did. We found that the individual angles of a hexagon are equal to 120 degrees. I'll do the calculation one more time just so you can see it. Hexagon is individual angles is 180 degrees times n minus 2 all divided by n. So the angle is 180 degrees times 6 minus 2 divided by 6. Our angle is going to be 180 degrees times 4 all divided by 6, which is 120 degrees. For a dodecagon, you need to remember what dodecagon is, and dodecagon is a 12-sided shape. Dodeca is 12. You don't necessarily need to draw these things out, but if you like the triangle method, you can. I'm going to cheat because my smartboard will draw it for me. That's a dodecagon. Okay, if I like the triangle way, I connect my vertices. And if I was using nice straight lines, which I should be, they're all going to connect in the middle. Okay, not pretty, should have been. Moral of the story is it makes 12 triangles. 12 triangles times 180 degrees in each triangle gives me 2160 degrees. And again, all the way around the center is going to be 360 degrees. So 2160 minus 360 degrees is going to be 1800 degrees in all 12 of my triangles. So I'm going to divide by 12 to get 150 degrees for each individual angle. If you like the formula better, and I like the formula better, it would be that the angle is 180 degrees times n minus 2, all divided by n. So each individual angle is equal to 180 degrees times 12 minus 2, all divided by 12. Or my angle equals 180 degrees times 10 divided by 12. And my angle is going to be 150 degrees. Okay, when I compare my angles, interior angles of my dodecagon with my interior angle of my hexagon, even though I've doubled the number of sides, I've not halved the angle measure. That's not how that works. Okay, so you can't just say, I know the number for 6 is 120, 12 is twice as much, so it must be divided by 2. That's got to be 60 degrees. It's not how it works. In fact, we're getting a bigger angle, not a smaller angle. So the more sides you have, the bigger the interior angles are going to be. So in this case, Melanie was not right. Okay, so this chart is going to show you the actual angle sizes for each shape. It says fill in the table below showing the size of each of the interior angles for each regular polygon. Okay, so for a triangle, n equals 3. For a square, n equals 4. Triangle has 3 sides, a square has 4. We're talking about regular, which means we can use our formulas. Penta means 5, so pentagon is 5 sides. Hexa means 6. Hepta means 7. Octa is 8. Nona is 9. Deca is 10. We usually skip 11 because there's not a lot of 11-sided shapes. But dodeca is 12. The angle side for each of them you actually need to calculate out. So we're going to do our individual angle formula. We know that 180 degrees times n minus 2 divided by n will tell us our angles, our interior angles. So for a triangle, n is 3. So 180 times 3 minus 2 in brackets, which is 1. So 180 divided by 3 is going to be 60 degrees. You're going to do that for each one of these. If you do all that work, and I'm just going to pick a few of them to do because I don't want to work them all out, and I actually don't have enough room, but you do for sure. Squares are 90 degrees. We'll do pentagon. Pentagon is 180 times n minus 2 over n. So 180 times 5 minus 2 over 5, which is 180 times 3 over 5. 180 times 3 over 5 is going to be 108 degrees. Okay, exact same process every single time. 6 we already did is 120. 7 doesn't work out nicely, it's a rounding one, 128.6. 8 is going to be 135. Nona is 9, so 180 times n minus 2 over n is going to be 180 times 9 minus 2 over 9, which is 180 times 7 over 9, and is going to equal 140 degrees. 10 is 144 degrees, and then we just worked out 12, 150 degrees. Okay, these are not things you need to memorize. You don't need to memorize them because the formula is really easy to use. All you're doing is putting in your side lengths. What you do need to memorize is this piece. For the name, how many sides does that mean? Once you know the side length, it's easy to calculate how big those angles are. The next question says, what regular polygon is approximated by joining the ends of the petals of the flower? What is the angle of each vortex? So first of all, we need to draw the polygon by attaching the ends of the petals of the flower. So the end to end, five-sided shape. They're approximately equal. This thing is 5 sides, which means it's a pentagon. Okay, that's the first part. What regular polygon is approximated by joining the ends? What's the angle at each vertex? If I want to know each individual angle, I'm going to use my individual angle formula. So my angle is 180 degrees times n minus 2 divided by n. So my angle is 180 degrees times 5 minus 2 over 5. My angle is 180 degrees. 5 minus 2 is 3, so times 3 over 5. Or my angle equals 108 degrees. Okay, if you're good at putting this in your calculator, if you don't need to simplify as you go, the minimum amount of work I want you to show me is this piece. Write your formula, fill it in, answer. Anything in the middle, I'm okay with you skipping out, but you need to write me which formula you're using with just the ends, fill it in properly, and then what your answer is. Okay, the next question says, the Giant's Causeway is an area in Ireland that's made up of about 40,000 columns of cooled lava that are mostly hexagonal columns. If the columns form regular hexagons, how many would join together to form a complete tiling, leaving no gaps between the columns? So this is a pretty common polygon question. It wants to know if you could kind of rotate these different shapes, could you get all the way around 360 degrees in a complete pattern, leaving no gaps between? So what this is saying is, you have a hexagon, and can you draw another hexagon beside it, and then another hexagon beside it, and make them match up, all rotating about a point? So if I took this hexagon and turned it, and then turned it again, can I eventually get back to my exact same original spot? Okay, there's a way of working this out without actually having to draw it, because drawing it is not always easy, as you can see from this beautiful diagram I've just done for you. And the way to figure it out is on the next page. So it says, in the previous example, you calculated that the interior angles of a regular hexagon are 120 degrees. So that was our individual angle is 180 degrees times 6 minus 2 divided by 6, because hexagon is a six-sided shape. So we calculate how many of these angles would fit around a common point. So if I'm talking about a point and rotating around it, to get all the way around is 360 degrees. If my interior angle measure divides evenly into 360 degrees, then I'm able to put that many of that shape around in the circle. So that's what it says. There are 360 degrees around a common point. Divide by 120. So 360 divided by 120 is 3. So 3 regular hexagons will fit perfectly around a central point. So 3 columns would have to join together to form a complete tiling with no gaps. Okay, so it takes, just like I drew in that last one, it takes 3 hexagons to get all the way around a circle if we're rotating about one common point. Okay, so it says example 2 shows that regular hexagons fit perfectly around a common point. This means that it would be possible to tile a floor with tiles in the shape of regular hexagons. What other regular polygons can be used to tile a floor? Give 2 possibilities, explain your answer. So it doesn't say which ones to try, so you could pick any of them. I'll do a few more than 2, just so you can see what this looks like. So if I want to talk about triangles, triangles are 3 sides. If I want to work out my individual angle, each individual angle is 180 times n minus 2 divided by n. So 180 times 3 minus 2 over 3. 180 times 1 over 3 is going to equal 60 degrees. So if 360 can be divided evenly by 60, then triangles will work. This does work. This is going to be 6. So it takes 6 triangles to rotate around a point. We can do the same thing for a square or a quadrilateral where n equals 4. 180 times 4 minus 2 over 4 is going to be 180 times 2 divided by 4. So 360 divided by 4 is going to be 90 degrees. If 90 degrees divides evenly into 360, then I can use squares to go all the way around the point. So 360 divided by 90 equals 4. So what that means is if I have a square and I rotate it about this point, I'm going to go this way, 90 degrees. Another square is going to be there. If I rotate it again, I'm going to end up down there. One more rotation makes my square there. 4 squares make a complete tiling. Okay, we'll do one more just so you can see when it doesn't work, so you can tell the difference. If we try a pentagon, penta means 5, so n equals 5. If I work this out, 180 times 5 minus 2, all divided by 5, is going to be 180 times 3 divided by 5, which is 540 divided by 5, which equals 108 degrees. So now if I do 360 divided by 108, I end up with 3.333 repeating. So this one doesn't work. It's not going to equal or be able to get all the way around without leaving a gap of 0.33333 of a pentagon. So 3 of them almost make it all the way around, but there's a space that's not filled because it doesn't divide evenly. So triangles work, squares work, hexagons work, and I think that's it probably for the shapes that we're dealing with. Okay, this last example, or last 2 examples, is working with kind of real-world examples of polygons. And the first one deals with octagonal houses. So houses that are not square, that have 8 sides. So it says octagonal houses were popular in the 1850s, and a number of historical octagonal houses exist in Canada and the United States. One such building is the Captain George Scott House in Wiscasset, Maine, in the States. So if the house is a regular octagon, what's the sum of angles at the vertices where the exterior walls meet? In this case, it wants the sum of the angles. So we're going to use our sum formula instead of our individual angle formula. So the sum formula said the sum of all of our angles is 180 degrees times n minus 2. We don't divide by the n because that's how we get the individual angles. This is talking about a regular octagon, which means we can use this formula. Octa means 8, so n is going to be 8. So in our formula, the sum equals 180 degrees times 8 minus 2, which means the sum equals 180 degrees times 6. And the sum is going to be 1080 degrees. So when we do this now, if you were going to do this in your calculator and you were good with the calculator and don't want to show the simplifying, you need to show me this step, your answer. I need to see what formula you're using, how you filled it in, and what the answer was in from your calculator. That's bare minimum for when you're showing your work. The next part says if the front wall of the house is 10 feet wide, what's the perimeter of the house? So how big is it all the way around? So we know we're talking about an octagon. So again, I'm going to cheat and I'm going to draw my octagon. This is saying the front wall of the house is 10 feet wide. And because I know it said it was a regular polygon in the beginning, I know that each of these sides are the exact same size. Perimeter is like you're building a fence. You need the length of all the way around. So this is 10 feet, this is 10 feet, 10 feet, 10 feet, all the way around, which means to find my perimeter, I can add up all my sides. Or because it's a regular polygon, I can take one side, I can do my side length, and I can times it by the number of sides. Either way is going to give you the same answer. In this case, though, my perimeter is going to be 10 feet times 8 equal sides. My perimeter is going to be 80 feet. The last one says the floor of a gazebo has the shape of a regular hexagon. The floor is painted in a pattern that divides the hexagon into triangles. Draw the lines needed to divide the floor into 6 congruent triangles. Congruent means exact same size. Okay, so I could do 6 triangles by going like this. 1, 2, 3, 4, 5, 6. Well, that last one's not really a triangle. But I could do crazy things. These are not congruent triangles because they're not all equally sized. If I want congruent or triangles that are the same size, I have to go opposite vertices and connect them. Okay, if you do a good job of it, your triangles should all be the same size. The next piece says, what are the interior angles of the triangles? Classify the triangles by side length. Okay, so I don't have a formula to find the interior angle of those triangles because I don't know if they're regular triangles or not. I don't know for sure if those side lengths are the same. What I do have is a way of finding how big the angles are in my hexagon. So if I go back to looking at just the hexagon, I can find each individual interior angle by using my interior angle formula. So the interior angle is 180 degrees times n minus 2 divided by n. So my angle is 180 degrees times 6 minus 2 divided by 6. My angle is 180 degrees times 4 divided by 6. Where my angle is 120 degrees. So each one of these here is 120 degrees. What I can say for sure is that when I draw my lines to make my triangles, because they're all crossing in exactly the middle, I know that those lines are splitting this angle exactly in half. So half of it's going to be on this side and half of it is going to be on that side. And so what that means for my triangles, and if I do it over here, half is going to be here, half is going to be here. So for my triangles, what that means is each of these pieces is going to be 120 divided by 2, which is going to be 60 degrees. And over here, each one of these guys is also going to be 120 divided by 2, which is going to be 60 degrees. So in my triangle, if this is 60 degrees and this is 60 degrees, I right now know that these two sides have to be equal to each other. That's an isosceles triangle property. If the angles at the bottom are equal, those two sides have to be equal as well. I need to figure out how big this top angle is in order to completely classify my triangle. And I do that because I know a triangle adds up to 180 degrees, and I'm going to subtract the two angles I know. And 180 minus 60 is going to be 60 degrees. And because now this angle matches all my other angles, this side matches as well. This is now an equilateral triangle, and I know that for sure now. Okay, so these are equilateral triangles. We couldn't just assume that to start with, we had to actually work it out. The last piece says, if the sides of the regular hexagon each measure 3 meters, what's the area of the floor? We're talking about area. We do not have a formula for area of a hexagon. That's not one of those area formulas that you guys should know. We do know that area of a triangle equals 1/2 base times height, or base times height divided by 2. Both are the same thing, just depends which way you guys learned it. And I know I can split my hexagon into triangles. So if I look back at my hexagon, and I'm going to split it into triangles. It's made up of 6 triangles. So what that means is if I can find the area of one of those triangles, I can multiply it by 6 to get the entire area of my hexagon. So when I look specifically at my triangles, I'm told in the question that the sides of the regular hexagon each measure 3 meters. So this is 3 meters, 3 meters, 3 meters all the way around. Which means this, if I'm talking about the bottom triangle of my hexagon, so this triangle right here is going to be this triangle. I know that that bottom side is 3 meters. From what I did in previous questions, I also know that this is 60 degrees and this is 60 degrees. This is going to tell me a couple different things. I need to find the base and the height of my triangle in order to use my area formula. So I know my base, this is going to be the base, but I need the height of this triangle. I don't have a way of finding it if I think of it as a big triangle. But that peak exactly cuts down the middle of my base, which makes this a right triangle. So I can use my right triangle and my right triangle rules in order to find this height over here. Because this splits exactly in half, the bottom part of my right triangle is half of the 3, which is going to be 1.5 meters. So now I want to use a right triangle formula to find this side length. Start by labeling my triangle. Across from my right angle points at the hypotenuse. Across from the angle I know points at the opposite side, which makes my third side my adjacent. I want a formula that has opposite and adjacent in it. Opposite and adjacent is the tan formula. So tan of my angle equals opposite over adjacent. So I know my angle is 60 degrees. So tan of 60 equals the opposite side, which is my height, over 1.5. To solve for this one, to get the h by itself, I need to multiply by 1.5 because right now I'm dividing by 1.5 and I always do the opposite. So h is going to be 1.5 times tan of 60. And my height is going to be 2.6 meters, approximately. So what this means, this is the height of my triangle. So if I go back to my big triangle, I now know that this is 3 meters all the way across, and I know that this is 2.6 meters tall. So my base and my height, I can use my area formula in order to solve for the area of one triangle. So my area equals my base, which is 3 meters, times my height, which is 2.6 meters, divided by 2. So 3 times 2.6 divided by 2 is going to be approximately 3.9. And I had meters times meters in my question, which means I now have meters squared in my units. This is the area of one triangle. We said originally there's 6 triangles in our hexagon. So we need to do times 6 to get the total area of the hexagon. And when we times this by 6, we end up with 23.4 meters squared. So this is the area of the whole hexagon. Okay, that's it. This is a skill you need to practice. Breaking your shape into triangles, using the triangles to find the area, and then using the area of one triangle to find for the whole shape, because I can guarantee there will be a question like this on your test. So make sure you know how to do this. Okay, the rest is for you guys to do. It's your practice section and then the chapter test section. Your test will be coming up soon. Make sure you're ready for it.